Hello everyone, this is introduction of a new unit for class 11th, which is Newton's laws of motion. So before discussing the Newton's laws of motion, the most important thing is force, because you know the force is something which can only cause motion. And now we are moving from kinematics to dynamics. So in kinematics we did discuss about motion, but we did not involve the cause of motion. But here in dynamics we will discuss about motion by taking into account the cause of motion, which is force. So let's understand what is force. So you might have studied in your junior standards as well that force is a push or pull. So basically force is any external agent which has the capability to change the state of a body. So if a body is at rest, the force has the capability to change the body to state to motion, or if the body is in motion, it has capability to take it back to the rest. So let's understand by a diagram. So this body is at rest on a surface, right? And now if I am applying a certain force here, body will acquire a velocity, it will come in motion. With respect to any reference point, you see the body will displace, and hence this force has caused motion. So force causes motion. And how? And let's say if I change this body and I place it, let's say this is a moving car, right? This is a moving car, let's say, which is moving in this direction, right? So this is moving with a constant velocity or maybe constant acceleration, but it has certain motion. But if I apply brake, what happens? After coming to some distance, it comes at the rest part, right? Here it stops. Basically means that this force, which is kind of retarding force, it had made this state from motion to rest for this moving car, right? So talking about force, if we talk about forces which are existing in nature, right? Forces which are existing in nature, they are classified into four major groups. First is gravitational force. Second is electromagnetic force. Third is nuclear force. And fourth is a general classification called weak force. So these are four major brackets in which forces around nature is classified. So let's talk one by one about all of these, right? So first is gravitational force. Gravitational force. So you might have studied gravitational force maybe before also. Here also we'll discuss it in very brief, that a body of mass m1 and mass m2, let's say, are separated by some distance r. There exists a attractive force between them, which is given by g m1 m2 by r square, where g is the universal gravitational constant denoted by 6.67 into 10 to the minus 11 Newton meter square per kg square. R is the distance and m1 m2 are individual masses, right? So now you can understand here that this gravitational force is an attractive force. So for m2, m1 is attracting m2, and for m1, m2 is attracting m1. So this is like the third law: to every action there is equal and opposite reaction. So both have tendency to attract each other with this amount of force, g m1 m2 by r square. And do understand that a gravitational force is a force by the virtue of mass, right? So the body which has mass will obviously attract other body which is having mass. The forces may be that negligible that it is not visible in day-to-day life, but the force which earth is applying on us as a gravity, that we can observe in day-to-day life, that is also a gravitational force. So let's say if one of the bodies is earth, so let's say earth is one of the body which have mass m, and there exists a small body of mass small m, and the distance, let's say this r is the distance from surface, right? So what is the force applied by earth? It is F equal to g m by r square. F equal to g m by r square. So F equal to g m by r square. Now you see this capital R is basically the radius of earth, and this r, So basically it should be R plus R, but R plus R is kind of equivalent to R because R is very, very small, right? So force applied by Earth on any body on its surface or nearby its surface is given by Gmm by R square, right? So this is the gravitational force of Earth. And if I apply it to the, find what is the acceleration caused, I can equate it to mg. And you know g is Gm by R square. And the value also you know, which is 9.8 meter per second square. So this acceleration is what? Called as acceleration due to gravity, which is caused by the Earth's gravitation on any body. So this is what we discussed as gravitational force. So next let's talk about electromagnetic force. So you know, this is the force which is because of the electromagnetic itself suggests it is because of the charges or because of electron, protons or the subatomic particles. So these force exist by the virtue of charge, right? So electromagnetic force is, again, there can be multiple varieties of electromagnetic force. So let's talk about one. For example, let's say one is electrostatic force. So you already know what is electrostatic force. So let's say if a charge q1 and charge q2 are separated by some distance r, there exists an electrostatic force between these two, which is given by F equal to k q1 q2 by r square. Looks like similar to the gravitational force we discussed. So that expression was given by Newton, and this expression is called Coulomb's law of electrostatic force. So you need not know in detail, just understand that if there are two charges separated by some distance, there exists an electrostatic force in between, and this force can be attractive or repulsive. This is another difference with respect to the gravitational force. Gravitational force were always attractive, but this can be attractive or repulsive depending on the nature of charges. So if both charges are like, they are same, then this force will be repulsive. If they are different, the force will be attractive, right? So this is what is given by, the force is given by this particular expression. So another type of electromagnetic force is, I can talk about one more type of force, which is, let's say, normal force. Normal force. So for what is normal force, right? What is normal force? So let's say there is a surface. There is a surface. And if I keep a block on this surface, so this block is somehow stable on this surface, right? So this basically means that surface is applying some force on this block is applying some force on the surface, they are balancing out each other, and hence this is stable. We can say that. So there also exists an electromagnetic force between the electron or subatomic particles of the block, which is at this lower surface, and also the particles at the surface. So there exists a electromagnetic vibration or force in between those electrons and the nucleus of surface, which is making this block stable on this surface, right? And the normal force which we talked about is the force which is surface is applying. So surface is applying a normal force, and to its response, obviously the block will also apply a downward force, and hence they are stable to each other. They are stable, right? So wherever there is a contact, there is an electromagnetic force. So before we discuss two forces which were gravitational and electrostatic, so they were non-contact forces. But you see there is a contact here. So this type of force is an example of contact force. You see there is a contact between the surface and the block. One more example we can take. Let's say tension. So tension force. So let's say if there is a string, right? If there is a string, this is a string, if this is hanged here, and if I apply a block here of mass, let's say 5 kg, anything, 5 kg. So now this string will taunt, right? It will get stretched by some negligible length, but it will exert a force by which it will stretch. It will experience a force because of this block. And that force is basically because of a tension created at this junction contact. So this is again an instance of electromagnetic force which is bringing a tension in this string. And if this string is massless, means this is having negligible mass, so the tension at every point will get stretched by some length, and at every point the tension will be same. So this is an example of tension force. Let's take one more example. So another example can be spring force. Spring force. So you already know what is a spring, right? You already know. So let's say this is a spring, and this is let's say a mass connected to this spring, right? Mass connected to this spring. So now, let's say if I shift this mass by some distance, let's say x, so the mass comes here now. So you see this string will get stretched here with a distance x. And again there is a contact between a string and the mass. So string will exert a restoring force to come back to its natural position. So this spring has a nature of elasticity, basically by which it will exert a restoring force to bring back to its natural or mean position, and that force is called force by the stretched spring, and which is given by force is proportional to x, and it is given by minus kx. And why minus? Because this is a opposing force, basically opposite to the displacement it is getting exerted. So if displacement is in this direction, the force is in this direction, so this is minus, and k is spring constant. K is spring constant, right? So these were the examples of what we discussed as a electromagnetic force. Now let's discuss the third category of force. Let's discuss the third category of force, which is nuclear force. Now, nuclear force basically applies between two bodies to hold each other, right? Applies between two bodies to hold each other, and it is very distance dependent. So let's take an example of a nucleus. So this exists inside the nucleus. This is a nucleus. So there exists a proton and neutrons. So if we talk about just electrostatic force, so you know gravitational force is negligible because the masses of neutron and protons are negligible. But if we talk about electrostatic force between two protons here, right? If we talk about electrostatic force between two protons here, now we can imagine that protons are of same charges, right? Positive charge. So if electrostatic force comes into account, there will be repulsion between protons because neutron is neutral, no charge. And there is a chance that this nucleus will outburst if only electrostatic force will be existing. So there exists a force in between these subatomic particles which is called nuclear force, which is holding these nucleus together. And this force only exists if the distance between these two particles are in the order of, I can say in the order of angstroms or Fermi meter 10 to the power minus 12 or something like that, very small distances between these two particles, and these type of forces were called as nuclear forces, right? And now the fourth type of force existing in nature is broadly classified as weak forces. So this is not what we need to discuss anything in detail. So this occurs in the case of decay reactions. Whenever there are reactions involving proton, neutron and exchange of that, this happens in those kind of reaction like beta decays or things like that. In those kind of decays, what happens is neutron basically breaks into protons and creates a particle, energy particle, which is called as antineutrino. Neutrino. Right. So this force which is responsible for this break, they are actually this weak force, right? They are this weak forces, which we do not need to discuss. If I talk about reverse situation, proton may also break into neutron and produce neutrino. So this neutrino and antineutrino, these are the species which are created. These are some energy species which are created, and the force responsible for this breaking is weak force, right? So this is the time we'll start laws of motion. So let's discuss the laws of motion. The first law, which is also coined as law of inertia. So what is the Newton's first law? We already know what is Newton's first law. So it states that an object at rest remains at rest, or an object in motion remains in motion, unless an external force is applied on it. So basically, if there is no external force, the object will have tendency to maintain its state, be it rest or motion, right? So let's say, if an object is moving, it will tend to move. It will never stop if any external body of force is applied to it, right? Or if an object is as rest, it will not move unless we apply any external force to it. This is what we call Newton's first law. Again repeating, if the sum of forces on any object is zero, the body will maintain its state of rest or motion. And that tendency of any object to maintain its state of rest or motion is what we call as inertia, right? The tendency of any undisturbed body to maintain its state of rest or motion is called as inertia, correct? So if I write mathematically, I can also write like, if external force equal to 0, so if the body was at rest, it will be at rest, or if it was in motion, it will be in motion. So this is what is called by Newton's first law, right? So you might have come across several situations where you would see Newton's first law applying, like if you are standing in a stationary bus and the bus starts suddenly, you see your body displacing towards the opposite side. Even if a bus is moving and suddenly it stops, you will see again a shift. So these are different kinds of inertia of rest, a direction. Or if you see a body, if you are in a cab or something, you see a cab taking a sharp turn, you see yourself experiencing a shift, that is inertia of direction. So the body which is moving or it at rest, it has a tendency that it will try to maintain its state of rest or motion unless anyone externally comes and disturbs that state. And that's what we call as Newton's first law, right? Now discussing about Newton's first law, we should understand that when we say a body is at rest or motion, it is depending on the reference frame, right? It is depending on the reference frame. Okay, let's say by Newton's law, if I can also say that if a body is at rest and still at rest, the external force is 0, right? Let's take an example. So let's say this is a Earth surface, right? And there was an elevator. This is an elevator. It was linked to some height, and let's say this link breaks. So what happens? Elevator comes down with G. The elevator comes down with G, right? And now, with respect to Earth, this elevator has an acceleration of 9.8, right? With respect to Earth, this elevator has an acceleration of 9.8. Now let's say there is an object hanging in this elevator. Let's say this is an object of mass m inside this elevator, hanging from the roof of the elevator. And now we have two observers. One of the observer is standing here inside the elevator, and one of the observer is standing at the ground. So this is observer number 2, and this is observer number 1. Right? Now tell me one thing. What are the forces on this M? The body M, what are the forces acting on it? So one force I can obviously say is the gravity, mg. And one force is the tension, because this is a string. So there are only two forces applying, tension and mg as of now. And according to observer 1, what is the state of that M? So if you are the observer 1, for you that M is not changing its position. It is always at the same position from you, and hence M is at rest. And if M is at rest, the observer 1 calculates and say that tension minus mg equal to 0, which basically says tension equal to mg, because the first law states that if sum of all the forces acting is 0, the object will continue to maintain state of rest or motion. So observer 1 gave its report that the mass m is at rest and tension is equal to mg. Now, according to observer 2, so observer 2 sees m and it says that m is in motion, right? Because with respect to observer 2, m is changing position, it is coming down, and he says that tension minus mg is not equal to 0 and hence tension is not equal to mg. The observer 2 says that. And now, one of them is wrong and one of them is correct. Or maybe both of them are correct. But basically there needs to be some change in Newton's first law to take this change or take this discrepancy observed by both the observers. Right? We cannot take both the observers as correct, because it's not possible that tension is equal to mg and tension is not equal to mg at the same time. One of them is wrong for sure. Who is wrong we will see later on. But let's understand that Newton's first law, the limitation of Newton's first law is it is frame dependent. It is frame dependent. So the limitation of Newton's first law, it is frame dependent or reference point dependent. Right? Now, since it is frame dependent, we can apply Newton's first law only in inertial frames. So there are two types of frames: inertial frame and non-inertial frame. And this is the frame where Newton's first law is applicable. Law is applicable. Newton's first law will fail to apply when we will talk about a non-inertial frame. Right? When we will talk about a non-inertial frame, Newton's first law will fail to apply. So Newton's second law, which is the law of momentum, it states that the rate of change of momentum is directly proportional to the applied force. So before discussing this law, let's understand what is momentum. So momentum is given by the product of mass and velocity. Mass and velocity. You know, mass is a scalar, velocity is a vector, and so momentum is a vector quantity. Momentum is given by the product of mass into velocity. And what is the significance of momentum? So basically, momentum indicates the amount of motion carried by an object. Momentum tells you that the object which is heavier is not always the one which can win every time. Even small masses but huge velocities can give you results. You take a bullet, you see how small is that, how small mass it has, but see the amount of velocity it has. You see a cricket ball, it's a very small ball, but if it has a huge velocity, it can cover significant distances. But if you take a large truck and with no velocity, it has negligible momentum, it has no effect, it can't change a state of anyone. So momentum basically indicates the presence of amount of motion by any object or a body, and it is the product of mass and velocity. Now basically, law of momentum states that the rate of change of momentum is indicated by P. P is how we indicate momentum, and rate of change of momentum is proportional to the applied force, right? So force is proportional to dP by dt, and you know P is mv. So now we are considering that the mass is constant, but there are systems where mass is also variable, like rocket propulsion, where it ejects a significant amount of mass every time it runs. But here we will consider the mass as constant, and we will take it out, and we will say that force is proportional to m dv by dt, and force is proportional to ma, and this proportionality is generally 1, so force equal to ma, F equal to ma, which is a very standard equation. And now with this equation, I can say that acceleration equal to force by mass, and this force is the net external force which is applied. So I can also rewrite second law as the acceleration of any object or a body is the ratio of the net force applying on it to the mass. The acceleration of any body is ratio of sum of all forces applying on a body divided to its mass in a inertial frame. Let's not forget that, in an inertial frame. Right. So now we discuss this law of momentum. Right. And now, what happens? Let's see how it relates to the first law. Let's say the force is 0. Net force on a system is 0. What happens? Acceleration will be 0 if net force is 0. And if acceleration is 0, basically means that if an object was stationary, it will be stationary. Or if it was moving with some velocity, it will not change its velocity. It will move with constant velocity. So, if it was in rest, it is in rest. If it was in motion, it will be in motion with constant velocity. There won't be any acceleration. Correct? So now we are able to relate the first law with second law. Correct? Now before dealing with the Newton's third law, let's think about this inertial and non-inertial. Till now we discussed these laws for an inertial frame, but let's say how we can extend these laws for a non-inertial frame. Right? So now the topic is dealing with non-inertial frames. So ideally, we discuss what is an inertial frame. A frame in which Newton's first law is valid is an inertial frame. Or I can also say that inertial frame is something which a frame has no acceleration. So if either a stationary frame or a frame with constant velocity is what is inertial frame. And now we will discuss about the how can we deal a problem with a non-inertial frame by taking into account. So let's say we have two frames, right? Let's say this S is a inertial frame. Inertial frame. And now this is again a S dash, which is a non-inertial frame. This is a non-inertial frame. And since this is a non-inertial frame, it will have some acceleration. Let's say it has acceleration something like A naught. So A naught is the acceleration of S dash with respect to S. Correct? A naught is acceleration of S dash with respect to S. Correct? And now let's assume that acceleration of A naught with respect to S dash and not A naught. Let's say there is a particle here. There is a particle. Now we will discuss about this particular particle. Right? We will discuss about this particular particle. So let's say this particle P, which is existing in this non-inertial frame, let's say it has acceleration A. So acceleration A is acceleration of P with respect to S dash. Acceleration of P with respect to S dash. Now, let's relate all these terms and let's understand how can we bring an inertial frame to a non-inertial frame and how can we deal with non-inertial frame. So can I write it like this? That acceleration of P with respect to S is basically acceleration of P with respect to S dash plus acceleration of S dash with respect to S. Correct? Acceleration of P with respect to S is equal to acceleration of P with respect to S dash plus acceleration of S dash with respect to S. Correct? You can relate. You can relate it like this. This is AP minus AS dash and this is AS dash minus AP, relative concept. And this is APS, right? And now, acceleration of P particle with respect to this S inertial frame, you know, this is given by what? This is given by F by M. And this we have assumed as A and this is A naught. So what is A now? A is F by M minus A naught. So F minus M A naught by M. F minus M A naught by M. So now you understand this A is acceleration with respect to a non-inertial frame which has this extra term M A naught. So if there won't be this non-inertial frame, acceleration will be force by mass. But with respect, because of this non-inertial frame coming into picture, which has acceleration a naught, we have this term ma naught. And this term ma naught is basically called as pseudo force. Pseudo force. So now you understand that to deal with any non-inertial frame, you need to bring an extra force into picture, which is called pseudo force. And after applying this pseudo force, you will be able to apply Newton's first and second law both. And now we understood that to apply these laws of motion to any non-inertial frame, we need to consider the pseudo force. And you see the magnitude of pseudo force is basically the mass of the body which we are considering, an acceleration of the frame, and it exerts in the opposite direction. If a naught is in the positive x direction, the pseudo force is in the negative x direction. So whenever you will see whenever you will make a free body diagram where you will indicate forces, and if your frame is a non-inertial frame, you need to indicate a new force called pseudo force. Let's take an example. So this, let's say this is a body, right? This is an inclined plane. This is an inclined plane, and this body is moving with a acceleration a, right? So now, if I say the forces on this body, and maybe I can also do something more to this. Maybe I can connect this to some pulley. Something like this I can say, right? Now I need to see what are the force acting on this. So one force is T. One is mg. One is normal because of this surface, right? But there is one more force which is acting. If you have to take all these forces and use Newton's law, which is force equal to mass into acceleration, we need to account one more force here, which is pseudo force, which is because of the acceleration of this whole system, because this is a non-inertial frame, because the frame itself is moving with a, and you need to take a pseudo force of magnitude mass into that acceleration and in the opposite direction, which means ma. And now you'll be able to use all those equations, and you'll be able to solve the acceleration, you'll be able to find velocity, whatever you need to find, you'll be able to appreciate now. So we'll solve more questions on this, how to deal with non-inertial frame, we'll understand better. Talking about Newton's third law, which is the law of action-reaction. Third law. So Newton's third law basically states that to an action, there is always an equal and opposite reaction, right? Let's say there are two masses existing, m1 and m2. This is 1 and this is 2, right? 1 and 2. So force F12 is force on 1 because of 2. F12 is force on 1 because of 2, which is, let's say, gravitational force. If I talk, this is m1 m2 by r square. This is r. And again, force on 2 because of 1 will be again g m1 m2 by r square. These two forces are equal in magnitude. What is the difference between these forces? One is in this direction, one is in opposite direction. So magnitude of these forces are equal, but direction of these forces are opposite to each other, and hence they are anti-parallel vectors. And this is what is Newton's third law, which says that to every action there is an equal, which will equal by magnitude, and opposite means opposite reaction means opposite by direction. So we'll solve more problems on this Newton's law in the coming lectures. Till then, thanks.